Just consider this diagram. I have taken an apparatus, and in the apparatus there are two solutions has been taken. One is your simply water, other one is sugar solution, and both the compartments are separated by SPM. Class, just now we studied that osmosis is movement of water molecules from region of lower concentration to higher concentration. Since again these two solutions are separated by SPM, so again the process of osmosis will take place and water will start moving from water side to sugar solution side. And class, in sugar solution side we have one frictionless piston over here. So as the water moves from water to sugar solution side, the piston is going to rise. And now here comes the definition of osmotic pressure. So what is the osmotic definition of osmotic pressure? It is the minimum mechanical pressure applied. I repeat, it is the minimum mechanical pressure applied on solution side, which is just sufficient to stop the movement of water molecule entering from lower concentration to higher concentration. Class, I again repeat, how do we define osmotic pressure? Osmotic pressure is defined as minimum mechanical pressure applied on sugar solution side, which is just sufficient to stop the movement of water molecule entering from lower concentration to higher concentration. That is your osmotic pressure. So, how can we define it? It is the minimum mechanical pressure applied on solution side, which is just sufficient to stop the movement of water molecule due to osmosis. So that is the definition of osmotic pressure. I repeat again. It is the minimum mechanical pressure applied on solution side, which is just sufficient to stop the movement of water molecule due to osmosis. Class, with this figure, we can also explain reverse osmosis. Now we are going to discuss reverse osmosis. That is simply your RO which you are using in your house. Every house now has RO, and RO is what? Reverse osmosis. So I am going to do some changes in this diagram. SPM remains here. Let us take seawater here and here plain water. Now listen carefully. If mechanical pressure becomes much greater than osmotic pressure. Class, due to osmotic pressure, water was entering from lower concentration to higher concentration. But if mechanical pressure becomes much greater than osmotic pressure, then the process of osmosis is reversed, and now water starts moving from higher concentration to low concentration, and that is called reverse osmosis. I repeat again. How can we define reverse osmosis? It is the minimum reverse osmosis. When mechanical pressure becomes much greater than osmotic pressure, then water starts moving from higher concentration to low concentration, and the process of osmosis gets reversed. Therefore, it is called reverse osmosis. Now, class, let us move to next topic in osmosis heading. We take up new word called tonicity. What is tonicity? Tonicity simply means concentration. So we are going to do a case study. What weight of RBC in different concentration? So I am going to make a diagram here. Just see. We are doing 3 experiments. Consider it RBC. In first case, RBC has been put in isotonic solution. Isotonic means same concentration. In the next case, RBC has been placed in hypertonic solution. Hyper means high. In the third case, RBC has been placed in hypotonic solution. Now we are going to find out what is going to happen to RBC if it is placed in isotonic, hypertonic and hypotonic solution. In the first case, since the concentration of both are same, therefore no effect. In the second case, your RBC is having lower concentration. Outside it is higher concentration. We know osmosis takes place from lower to higher, so water will move from RBC to outside, and as a result, cell will shrink. In the last case, RBC has been placed in hypotonic solution. Hypo means less, so RBC has higher concentration, and outside it is lower concentration, so water starts moving from lower to higher. So water will enter into the cell, and ultimately the cell will swell and finally burst. So this is the fate of RBC in different concentrations. Now class, we'll move to numerical part of osmotic pressure. Bent-Top theory for osmotic pressure. Bent-Top suggested that dilute solutions behave as an ideal gas. Therefore, ideal gas equation is applicable. In class 11, we studied ideal gas equation as PV equal to nRT. In this case, we will write it pi V equals to NBRT. So what is pi? Pi is osmotic pressure in ATM. V is the volume of solution in liter. Class, remember, volume of solution should always be in liter. NB, number of moles of solute. R is your universal gas constant, and we all know that we are going to use 0.0821 liter atmosphere inverse mole inverse value of R, and T is your temperature in Kelvin. Class, let us take this equation 1. In the second case, if you divide NB by V, so number of moles of solute upon volume of solution liter, that gives you molarity. So we can write pi equal to CRT, where C is your molarity, and that too in mole liter inverse. Class, we can do one more thing. Number of moles of solute is WB upon MB. Let us put volume here. R into T. Class, just see, weight of solute upon volume of solution liter, that gives you density. So pi equals to D by MB into R into T. So that becomes our equation number 3. So we get 3 derived expressions for osmotic pressure. And now we'll be doing numerical. The question is, find osmotic pressure developed in 0.1 molar glucose solution at 27 degrees centigrade. So the concentration has been given to us. So we'll use formula number 2. Pi is your osmotic pressure. We are going to calculate. Concentration is 0.1. R 0.0821 into temperature is 27 degrees centigrade. So converting it to Kelvin, it gives us 300. And class, so I already told you that this number multiplied by 300 gives you 24.63. So 0.1 multiplied by 24.63 gives you 2.463 atm pressure. So this is the way you can solve. We can go for another numerical. Find osmotic pressure developed when 36 gram glucose, molecular weight unit, dissolved in 200 gram solution at 27 degrees C. So class, will use the basic formula pi v equals to nb into r into t. Just do one correction, make it 200 ml solution. So, pi we are going to calculate. Volume of solution is 200 ml, but we are supposed to put in liters. So 200 upon 1000. NB, number of moles of solute. 36 is the weight of solute. Molar mass is 180. R 0.0821 and temperature again 300. 5. Again 5. This 5 goes with this 5. So we are left with 5 equal to 24.638. So in this way we can solve numericals on osmotic pressure. So now class, we have completed our all the 4 qualitative properties. First, relative lowering of air pressure, that was taught in the class. Elevation in boiling point, depletion in freezing point, and the last one is your osmotic pressure. So these 4 are the qualitative properties. Class, in the next lecture, we are going to work on abnormal molar masses. In our next class. We have studied all these 4 qualitative properties, and in all these 4 qualitative properties we find MV, that is molar mass of solute. So class, whenever we calculated molar mass of solute by using all these 4 methods, sometime molar mass was supposed, which came out with the help of solving numerical, sometime it was high, sometime it was low. Why it was high and why it was low, that can be understood from here. Plus, we all know that colligative property is directly proportional to number of moles of solute particles. If NP increases, then Cp is definitely going to increase. I repeat, if NP, number of moles of solute increases, then colligative property also increases. If NP decreases, colligative property also decreases. But why increases? During dissociation, we find number of moles increases. And during association, we find number of moles decreases. How they increase and how they decrease, we'll be taking up on in next lecture. But now, let us first find out what is going to happen to molar mass of solute. Number of moles of solute particle is directly proportional to colligative properties, and colligative properties are in turn inversely proportional to molar mass of solute. How? You see it. This relative lowering of air pressure, and it is indirectly proportional to molar mass of solute. Elevation in boiling point, again inversely proportional to molar mass of solute. Delta TF again inversely proportional to molar mass of solute, and osmotic pressure is also inversely proportional to molar mass of solute. Hence, we can say number of moles of solid particle is directly proportional to colligative properties, and colligative properties inversely proportional to molar mass of solute. During dissociation, NaCl, when it dissolves in water, if I take 1 mole of NaCl, if I am dissolving in water, it gives me 1 mole Na positive and 1 mole chloride negative. So we started with 1 mole and now we are ending with 2 mole. Therefore, during dissociation, Nb increases, and if Nb increases, then colligative property also increases, and if colligative property increases, then molar mass decreases. So, whenever there is dissociation in the solute in water or in any given solvent, if number of moles increases, then definitely molar mass which we are going to calculate will be always less than expected. During association, whenever acetic acid is dissolved in benzene, it dimerizes. You see. Sorry. Right. We have taken 2 moles of acetic acid, and once the dimerization takes place, how much mole we are getting? 1 mole. So during association, number of moles of solid particle decreases. Hence we can say Nb decreases, Cp decreases, and molar mass is more than expected. Hence, during dissociation, molar mass is less than expected, and during association, molar mass is more than expected.